Oh, did you go?
Yeah, I'm trying to find
Welcome to the security seminar here at Purdue University. It's my great pleasure to introduce today's speaker, Dr. Ting. Ting received a PhD in computer science from University of Illinois at Urbana-Champaign in 2003, and currently he's a faculty member at North Carolina State University. His research interests include automated trust negotiation, trust management, privacy policy specification and management, and also data privacy. Here's Ting.
Right. So thank you. Thank you very much. It's really a great pleasure to give a talk in the security seminar. And today I'm going to discuss how to define compromised sensor nodes in wireless sensor networks. So this is a joint work with Qin Zhang and Peng Lin at our department. So recently there's a huge interest in wireless sensor networks. So in wireless sensor networks, we pretty much deploy low-power, inexpensive sensors in large geographic areas. So the property of wireless sensor network is that after deploy it, those sensors are going to self-configure themselves and configure into a network. So because of this property, it has been envisioned to have a very broad applications. So for example, we can use it for target tracking, battlefield surveillance, and environmental monitoring. So in particular, because once you deploy it, it's going to self-configure into one network, it is very suitable for event tracking in open hazard environments. Okay. But on the other hand, wireless sensor networks have imposed great security challenges. In particular, because sensors are deployed in open systems, they are very vulnerable to physical attacks. Anybody can just access the sensor physically and may try to compromise the sensor. So in the worst case, the attackers may just extract all the key materials. So in this case, the attacker may just completely impersonate that compromised nodes and introduce arbitrary false information into the system. Okay? So in that context, cryptographic techniques may not be helpful because the key has been compromised. If you want authentication, I can do authentication. Okay? I can also encrypt my data as you want. Okay? So how are we going to identify compromised sensors? That is the topic of this talk. Okay? So here's the outline of the talk. So first, I'm going to present a framework for identifying compromised sensors in wireless sensor networks. So our approach is not specific to any applications. Instead, we want to extract the intrinsic relevant properties so that we can run algorithms to identify compromised nodes. Okay. Then we're going to present the design of identification function. We show that this function is optimal in the sense that we're going to identify the largest number of compromised nodes without introducing any false positives. Okay. Later on, we're also going to present some techniques to further increase the number of compromised sensor nodes in the cost of introducing some false positives. I'm going to show some experiment results to show the effectiveness of our approach. And finally, I'm going to conclude this talk and briefly discuss the directions for future work. Okay. So the problem of compromised sensor nodes has been recognized in the literature, and there has been several approaches has been proposed. So basically, those approaches have been can be divided into two categories. So in the first category, people try to detect and tolerate the false information introduced by compromised sensor nodes. For example, in data aggregation, we may introduce redundant sensor nodes, or we may do some random sampling. So in hoping that if we find some information which is very different than what expected, then I just filter out those information. So hopefully the information I got finally does not deviate too much from the true information. Okay? So in this approach, however, we cannot identify precisely where this false information is introduced. We may not be affected by the false information, but we don't know exactly which node are compromised. And in the second category, we call it alert-based approach. So in this kind of approach, the application introduces some specific detection mechanisms so that sensors may observe each other's behavior. Okay? If I observe something weird, then I may just send alert to the base station, say, hey, look how this guy is bad, probably bad. Okay? So by looking at those alerts, we may be able to pinpoint exactly which node is compromised. But the problem is that good nodes may issue alerts against bad nodes, but a bad node which is compromised may also issue false alerts to mislead the judgment of the base station. Okay? So when we receive a bunch of alerts, we really don't know which one is valid, which is not. How are we going to reason about it? How can we know which node is compromised, given a bunch of alerts? Some are false ones. So when we first look at the problem, the first thought in my mind is that, well, wait a minute, you have a bunch of nodes talking to each other, and you have alerts issued against each other. So this is quite similar to like online auction community and eBay. People get service from each other, then issue feedback, evaluate others' service. A lot of work has been done on reputation-based trust management in P2P systems and online auction communities. So can we just apply those techniques directly into valid sensor networks? Okay. And after further investigation, we found that in sensor network, there are some unique properties that are quite different from the P2P system or online auction communities. So first thing is that in a P2P system, any two nodes can talk to each other. There's no restriction who you can talk to, who you cannot. But in various sensor networks, we have some deployment topology. A node may only interact with others around it. We cannot have interaction between two nodes that are very far away from each other. Okay? So in other words, we have some topology there for detection. Okay? So because of the topology, local majority is a severe problem. Because if I know that this node can only talk to 3 nodes, then I can compromise these 3 nodes. Then I can just badmouth this specific node. Okay? And so that is challenging here. But on the other hand, in P2P systems or online auction communities, every node is really selfish. Okay? I want to get the best from the system, and I don't want to jeopardize my own benefit. Okay? But in sensor networks, it's more or less a distributed system. Okay? All those nodes collaborating with each other try to achieve one common goal. So in that sense, it's maybe possible to achieve a global optimal by sacrificing some specific nodes in the system, in the sensor network. This may not be possible in a P2P system. Okay? If I have to issue alert and sacrifice myself, then probably I'm not going to do that, okay? Because I want to protect my own benefit. Okay? So look at this uniqueness of sensor networks. We observe that they bring both challenges and opportunities to identify compromised nodes. So we want to take advantage of those properties. So next, I'm going to present an application-independent framework for identifying compromised sensor nodes. Okay, so in this framework, we make the following assumptions. The first one is that because we are targeting at alert-based approach, so we assume that there exist some application-specific detection mechanisms. So in other words, we have some way that for one node observe another node's behavior. Okay? So that is provided by the application. And second, we focus on static sensor networks. That means once a sensor is deployed, its position does not change dramatically. So one implication of this assumption is that the observation relationship between different sensors does not change once you deploy the sensor network. Okay? And then we assume there exists some basic security primitives to protect message confidentiality integrity. So when a sensor issues one alert to the base station, we know that it is not compromised, and we know who issued this alert.